Hello and welcome to Mr. Tompkins EdTech. This series of videos provides work solutions for the GCSE Maths topic test produced by AQA. This video is sequences. Whilst these topic tests make excellent exam preparation and revision material, regardless of which exam board you're sitting, they are particularly useful for students studying for AQA as they are prepared by the same team who will be writing your papers in the summer. They will work best if you try and answer the questions yourself before watching the video. The topic test papers can be downloaded from this address, which I've also linked in the description below. They'll require a teacher account to access, so either ask your maths teacher to download and share them with you, or alternatively you can try pausing the video and attempting the question first before pressing play again to listen to my solutions. Check this playlist for all the other topics I've covered. I'm busy recording all of these topic tests, so if the particular topic you're looking for isn't there yet, why not drop me a comment below with your request and subscribe to my channel to receive notification of future uploads. If there is anything you don't understand, please ask in the comments. Make sure you mention the question number and try to be as specific as possible. I try to answer all questions promptly, especially around exam times. If you found the video useful, please do hit the like button, as this really helps me out. You might also like to check out my exam paper walkthroughs covering all the recent papers and practice papers from AQA. Just click on the card appearing at the top of the screen now. Okay, let's get started. Before we get started, I'm just going to show the blank question paper. So if you don't have a copy, you can now pause it and have a go at the questions first. And then once you're finished, you can start again and look at the answers. Okay. Welcome along to another AQA topic test. Today we're looking at sequences. This is a foundation tier paper, but it would be a good introduction also to higher tier students. Okay, so before we get started on the actual questions, let's have a quick look at all the different types of sequences that you need to know for GCSE. Now first off, we've got three kind of number property sequences that you need to know about. Square numbers are the numbers 1, 4, 9, 16 and so on. Now they're all the numbers that you can get by multiplying a number by itself, or another way of thinking about it is that you can arrange that number of items of things into a square. So you can take 4 circles and arrange them into a square shape, but you can't do that with 5 things or 6 things or 7 things or 8 things, but you can do it with 9 things. Okay, so either remember it like that, or you can think of it as 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9 and so on. So the next square number in this list is going to be 5 times 5, which is 25, isn't it? Okay, similarly cube numbers is numbers that you can take that number of little cubes and arrange it in a cube. So the cube numbers are 1, 8, 27, 64 and so on. You can also think of these as 1 to the power 3, or 1 times 1 times 1 is 1, 2 times 2 times 2 is 8, 3 times 3 times 3 is 27, 4 times 4 times 4 is 64. So the next one in this list would be 5 times 5 times 5, which is 125. Okay. Next, triangle numbers. You can think of triangle numbers as the number of items that you can arrange into the shape of a triangle. So you can take 3 things and arrange it into a triangle shape, or you can take 6 things and so on. Think about 10-pin bowling, or if you play pool or snooker, then you get 15 balls in the little triangle at the start. These are all triangle numbers. So and you can look at the pattern that you get from one term to the next. So the difference between 1 and 3 is 2, the difference between 3 and 6 is 3. You can see it's increasing by 1 each time because you're adding a longer line to make your next triangle number up. So my next number after that is going to be adding 5, which is going to give me 15, isn't it? Okay. Now, as well as those kind of number property sequences, we need to know about linear, quadratic, Fibonacci, and geometric sequences. Linear sequences have what we call a common difference. If you look at the distance between 2 and 5, they are 3 digits away from each other, or 3 numbers away from each other. 8 take away 5 is 3, 11 take away 8 is 3. So all these have got a common difference of 3, so we can get the next one by adding 3 onto the previous one. 11 plus 3, the next one is going to be 14 and so on. Okay, now quadratic sequences we say have a common second difference. Now if I have a look at the difference between these numbers, they're not the same. 9 take away 2 is 7, 18 take away 9 is 9, 29 take away 18 is 11. So it's going up by 2 each time. But if you have a look at the difference of their differences, 9 take away 7 is 2 and 11 take away 9 is 2. So they have what we call a common second difference, or the difference of their differences is the same all the way up. So that's how you can tell if it's a quadratic sequence. A Fibonacci sequence is a special sort of sequence where the next term in a sequence you get by adding the two previous terms together. Now a classic Fibonacci sequence starts with two ones, and then if you add those two ones together you'll get the next number in a number in the sequence, which is 2. And if you add the 1 and the 2 together you'll get the next one, which is 3. And if you add the 2 and 3 together you'll get the next one, which is 5, and so on. But actually you can have a Fibonacci type sequence by picking any two starting numbers. You'll get a different sequence of numbers, but we say it's a Fibonacci type sequence. But the classic Fibonacci sequence starts with two ones. Finally, geometric sequences, they don't have a common difference, they have a common ratio, which means you can get the next term by multiplying the previous one by the same number. So if you have a look at this one here, if I multiply 3 by 2, I get 6. 6 times 2 is 12, and 12 times 2 is 24. So a geometric sequence has a common ratio, not a common difference. So you can multiply them by the same number each time to get the next one in the sequence. So the next number in my sequence here is going to be 48. Okay, I didn't do that for my last two, did I? So the next number in my Fibonacci sequence, 3 plus 5, is going to be 8. And the next number in my quadratic sequence, I'm going to get by adding 13 to 29. 2 more than 11 is 13. 13 plus 29 is 42, isn't it? Okay. So you should be aware of each of these sequences and be able to spot which sort it is and be able to work out the next term, given that you know it's any one of those types of sequences. Let's have a quick look at question 1. Here is a pattern of calculations. I've got 7 times 9, and that's 63. 77 times 99 is 7623. 777 times 999 is 776223, and 7777 times 9999, I can't remember how many nines that was, is equal to 777622223. Can you see any patterns there? Okay, well obviously that we're increasing the 7s and the 9s by 1 each time. But what's going on in the number for our answer? This 6 seems to stay the same all the way down, and the 3 stay the same all the way down, but we seem to be getting like 1 extra 7 each time and 1 extra 2 each time in the middle, don't we? Okay, so I assume then if we're going to go from 4 7s to 6 7s times 6 9s, we're going to have to go down another 2 patterns then, aren't we? So next pattern down, oops, that's a bit chunky. So next pattern down would be 5 7s, and then 7 7 7 7 7 times 9 9 9 9 9. What's that going to be then? So we can see that each time you'll get one more 7. So I'm expecting it to be 7 7 7 7. And then we're going to have that 6 that doesn't seem to change. And then we're going to get 1 extra 2. So we're going to get 2 2 2 2, and then a 3 on the end. Okay, so you can see my 7s I've got 1 extra, my 2s have got 1 extra, and my 6 and my 3 remains unchanged. Okay, so that's with 5 digits. Let's now have a look at 6 digits. 7 7 7 7 7 7 times 999 999. Okay, again, I'm going to increase the number of 7s by 1. I've got 4 in my last number, so let's have 5 this time. Oops, why did I write 5 there? 5 7s, and then I'm going to have a 6. I'm going to do 5 2s, and then I'm going to do my 3 on the end. So I've increased the number of 7s by 1, I've increased the numbers of 2 by 1, but I've retained this single 6 and single 3 on the end. Okay, so that's what I think the answer is going to be. So my answer 7, 7, 7, 7, 7, 6, 2, 2, 2, 2, 2, 3. Now I think if I actually type that into my calculator, it might blow up. Hold on, let's have a look. So if I tap 777 times 999 times 999 into the calculator, you can see I get an answer which is written in standard form. It's run out of digits to display it, so it can't do it all. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 digits, and I think my calculator can only go up to 10. So we're just going to have to trust in the pattern and hope that's the right answer. Question 2. A sequence of numbers is formed with 1 1, 2 2s, 3 3s, 4 4s, and so on. Work out the 100th number of the sequence. Okay, so let's think this through. I've got 1 1, so I'm going to write down 1. Then I've got 2 2s. Now if I add that to the number of 1s I've got, then 1 plus 2 is 3, isn't it? Okay, and then so that's my second number of 2s, takes me up to 3. Now if I add on the number of 3s, then that is going to be those numbers there. 3 3s, which takes me to 6. And then if I add on my 4 4s, how many have I got now? I've got 10. Do you recognize this sequence of numbers yet? Okay, next one is going to be add 5 5s, which is going to take me to, it's going to take me to 15. 6 6s is going to take me to the 21. 7 7s is going to take me to 28. So 3 4 5 6 7. 8 8s is going to take me to 36. 9 9s is going to take me to 45. 10 10s is going to take me to 55. 11 11s is going to take me to 66. 12 12s is going to take me to 78. 13 13s is going to take me to 80 91, and then 14 14 is going to take me over it, isn't it? It's going to take me up to 105. So that means the 100th term has got to be in this group of 14s here. So it's going to be a 14. Okay, so just observe that those numbers formed there are actually the triangle numbers. I don't suppose you'll remember it all the way up to the 14th triangle number though, so I'm not sure that will help too much. But anyway, the answer is 14. Question 3. Here is a linear sequence. The first 2 terms are missing. Yep, they are. I've got the numbers 3, 9, 15, 21, 27. Okay, now we saw earlier that linear sequences have what we call a common difference. So that means that there is if you look at the one term and you take away the previous term, you'll get the same number. So if I look from 3 to 9, 9 take away 3 is 6, and that's going to be the same as 15 take away 9, 6. 21 take away 15 is 6. So how do we describe how the sequence is building up? We can say that the next term is 6 more than the previous term. Or it's an add 6 sequence, I suppose. It's an easy way of putting it down. Right, and then what does part B say? What is the first term of the sequence? Okay, so we need to kind of work backwards here then, don't we? So if we know that we are adding 6 each time, if I want to go back a term, I'm going to have to subtract 6, and aren't I? So what's 3 subtract 6? 3 subtract 6 is minus 3, isn't it? So in here should be a minus 3. And then I need to subtract another 6 to go from there to there. So what's minus 3 take away another 6? Negative 3 take away 6. That's going to be negative 9 then, isn't it? So negative 9 goes there. So what is the first term of this sequence? It is negative 9. Question 4. Here are the second and third terms of a linear sequence. So again, this is a linear sequence, so there should be a common difference between the numbers. So when you take one and you subtract the next one, you should get the same equal number. So 17 subtract 12 has got a common difference of 5. So the next one in their sequence is going to be 5 more than 17. That's going to be 22. And the one below it is going to be 12 subtract 5, which is going to be 7. Okay? Work out the mean of the first 4 numbers of the sequence. Okay, now to find a mean, you just need to take all the values, add them up, and divide by how many you've got. So I can do mean equals 7 plus 12 plus 17 plus 22, all divide by 4. So what's that then? 7 plus 12 is 19, plus 17 is 29, 36, plus 22 is 46, 56, 58. So it's going to be 58 divided by 4 then, isn't it? 58 over 4. 4's into 58. 4's into 58. 4 into 5 goes once, remainder 1. 4's into 18 goes 4 times, remainder 2. So that's 14 and 2/4 then, isn't it? Or 14 and a half. So 14 and a half. Okay. Now, actually, you could have done it a lot easier. You could have just added those two together and divided by 2. That would have given you the same result, because the mean of those two numbers is going to be the same as the mean of all 4 numbers. So yeah, but that's a by the by. We've done it now already. This week's topic test was a special request from one of my patrons over at patreon.com. I'm really grateful for the support you guys provide for me. Really appreciate it. Now, if you like my content and you would appreciate gaining early access to my past paper walkthroughs, why not check it out at patreon.com/Mr. Tompkins EdTech. Now, back to the maths. Question 5, write down the next term of each of these sequences. And I've got 5a, which is 4, 9, 16, 25, 36. Do you recognize that sequence? If we pull up our list of all the sequences that we need to know, I hope that you can recognize which one it is. It should be this one, shouldn't it? The square numbers. You've got the 1 isn't there, but you've got the 4, 9, 16, 25, 36, which is 6 times 6. The next one in this sequence is going to be 7 times 7, isn't it? Which is 49. So my next number is in this sequence is 49. Okay, so have a look at B. This is going 1, 1, 2, 3, 5, 8, 13. Do you recognize that one? Let's pull up our list again here. Now, hopefully you can recognize this as a Fibonacci type sequence. In fact, it is Fibonacci sequence because it's starting with 2 1s. So 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, and so on. So the next number I'm going to get by taking these 2 terms, adding them together, and that is going to give me the next term in my sequence. So 8 plus 13 is 21, and that's going to be my answer, isn't it? 21. Question 6. The nth term of a sequence is 7n minus 3. Work out the first 3 terms of the sequence. Okay, now n is the position of the sequence. So for the first term, n is 1. For the second term, n is 2. And for the third term, n is 3. And we can use 7n minus 3 to generate the term. What we've got to do is take its position, 1, and imagine it there where the n is. Okay, so if I take n as 1, then 7n minus 3 is going to be 7 lots of 1, 7, take away 3, which is 4. Okay, next, take the next number for n is 2, and imagine it where n is. 7 times 2 is 14, take away 3 is 11. And then, 11. And then finally, take n is 3. Imagine it where the n is in that equation there. So 7 lots of 3, 21, take away 3 is 18. So our 3 terms are going to be 4, 11, 18. Okay, then it says, which term of the sequence has a value of 109? Now we know that the nth term of this sequence is given by the formula 7n minus 3. So what we're saying here is that 7n minus 3 is equal to 109. So we've basically formed an equation in n that we can now solve. So let's add 3 to both sides of this equation. That should get rid of that 3 there and leave me just with 7n on this side. 109 plus 3 is 112. And then we're going to have to divide both sides by 7, aren't we? Divide by 7, divide by 7. And it's going to give me the value of n. 7's into 112. 7's into 1 don't go. 7's into 11 go once, remainder 4. And 7's into 42, that goes 6 times. So I've got n is equal to 16. Question 7a, work out the next term of this quadratic sequence. Now you remember from earlier we said that quadratic sequences have a common second difference. So if I'm going to go underneath here because it's got a bit more space. If I take from 6 to 10, 10 take away 6 is 4. 16 take away 10 is 6. 24 take away 16 is 8. And 34 take away 24 is 10. So you can see that the common difference, 6 take away 4 is 2. 8 take away 6 is 2. 10 take away 8 is 2. So the common second difference is 2. So that means my next term I'm going to get by adding 2 more than the last term that I used. So I added 10 last time. 2 more than 10 is 12. So if I add 12 onto 34, that's going to take me up to 46, then, isn't it? So my answer then is going to be 46. Okay, 7b, work out the next term in this geometric sequence. Okay, pulling up the list from earlier, geometric sequences we said had a common ratio. So these are a common multiplier then between the two numbers. So what do you have to multiply 3 by to get 9? So 3 times 3 is 9. Now if I take 9 and times it by 3, I get 27. If I take 27 and times it by 3, I'm going to get 81. Apparently if I take 81 and times it by 3, I'm going to get 243. So to get the next value in this sequence, I need to multiply 243 by 3, don't I? I have to times that by 3 to get the last number there. Okay, so what is 243 times 3? Well, let's multiply it up. I tend to use Napier's bones when multiplying. So 2, 4, 3 across the top times 3. So 2 times 3 is 6. 4 times 3 is 12. 3 times 3 is 9. And then we just add up along the diagonals then, don't we? If you've ever used this method before, you know it's all very easy. So that gives me 9, 0 and 2 makes 2, 1 and 6 makes 7. So that comes out to be 729. 729. Question 8. Here is a sequence. It's got 15, 13, 11, 9, 7. Circle the expression for the nth term of this sequence. Okay, so what sort of sequence have we got here? If you look at the difference between 15 and 13, I'm going down by 2 there, aren't I? And the same from 13 to 11 and 11 to 9. So each one of these I'm subtracting 2 to go from one term to the next. So what sort of sequence is that? Common difference means it is a linear sequence and it's going down in negative 2's. Now, that tells me that the nth term has got something to do with negative 2n. If it's going down in 2, it's got to be do with negative 2n. So it's not going to be that one. It's not going to be that one. It could be that one, or it could be that one. So it's out of those two. Okay, let's see if we can finish this off then. So minus 2n, let's imagine I knew what the numbers of n were, like 1, 2, 3, 4, and so on. Then minus 2n would be minus 2, minus 4, minus 6, minus 8. But I don't have minus 2, minus 4, minus 6, minus 8. I've got 15, 13, 11, 9. So if you look at the numbers generated by minus 2n, minus 2, minus 4, minus 6, minus 8, and the numbers we've actually got, 15, 13, 11, and 9, each one of these is 17 more than our sequence minus that we get from minus 2n. So this must be 17 minus 2n. So 17 take away 2 lots of 1 is 15. 17 take away 2 lots of 2 is 13. 17 take away 2 lots of 3 is 11, and so on. So our real answer is that one there then, 17 minus 2n. Question 9. The nth term of sequence A is 2n plus 3, and the nth term of sequence B is 5n minus 4. Work out two terms that are in both sequences. Okay, so I'm just going to write down A and B here. Let's take some different values of n. So 1, 2, 3, 4, 5, 6. Don't know how many I'm going to need in order to work these out. Now, if you remember, A is 2n plus 3, and B is 5n minus 4, then, isn't it? So when n is 1, 2n plus 3 is going to be 2 lots of 1, 2 plus 3, which is 5. And then 2n plus 3 is going to be 4 plus 3 is 7. And then it's going to go up in 2s each time, isn't it? 9, 11, 13, and so on, 15. And for 5n take away 4, when n is 1, I'm going to get 5 times 1, 5 take away 4 is 1. When n is 2, 5 times 2 is 10, take away 4 is 6. And then it's going to go up in 5s, isn't it? So that's going to give me 11, 16, 21, and 26. But I've gone further than I need to because I've already spotted that I've got an 11 in both lists already. So work out two terms that are in both sequences. Okay, we've only got one, so we need to go a bit further then. Okay, so let's just add a few more on. 7, 8, 9, 10. We're going to have to go that far. So this one was going up in 2s, wasn't it? 17, 19, 21, 23. Okay, I found another one then. So I've got 21 here and 21 over there. So that is 11 then is in both lists, and 21 is in both lists. Question 10. The nth term of a sequence P is an plus b, and the nth term of sequence Q is bn plus a. Show that the sequence both start with the same term. Bit of a weird question, algebraic sequence. So I've got an plus b is my first term of sequence B. So for first term, n is going to be equal to 1, isn't it? Okay, so for sequence P, that is going to be a lots of 1 then plus b, so that's just a plus b. And for Q, it's going to be b lots of 1 plus a, which is, well, b plus a, which is the same thing as a plus b then, isn't it? So those two you can see are the same. Okay, and then part B, it says the second term of the sequence P equals the third term of sequence Q. Show that a is equal to 2b. Okay, so the second term of sequence P, second term of P is going to be, well, it's going to be an plus b when n is equal to 2. So it's going to be a lots of 2 plus b. In other words, it's 2a plus b, isn't it? Okay, and my third term of Q is equal to bn plus a, where n is 3. So it's going to be b lots of 3 plus a, which is a plus 3b. Okay, so, and we're told that these two things are equal to each other. So 2a plus b is equal to a plus 3b. Okay, so can we simplify that a bit? We can take off b from both sides, subtract b, that will cancel with that, and then that will give me, running out of space, 2a is equal to a plus 2b. And then if I take a off both sides, subtract a, that will cancel with that, and that will leave me with a is equal to 2b. Oh, that's what I asked to show, wasn't it? A is equal to 2b. So it kind of almost fell off the bottom of the paper there, but we seem to have got to the end. Well, that's that. I hope you found the video useful. If you did, please hit the like button and consider subscribing to my channel. Also, check out the playlist on the right for more topic tests, or the one down below for past papers. See you again next time.